What if I told you that summer once simply vanished? That in relatively modern times, an apocalyptic climate disaster killed 1 million people, caused global famine, and rewrote human history. Yet most people have never even heard of it. This isn't science fiction, this actually happened. Imagine waking up on a summer morning, pulling back your curtains, and instead of seeing the golden glow of sunshine, you're met with an eerie darkness, a sky tinted blood red and snowflakes dancing in the June breeze. No, this isn't the opening scene of some apocalyptic Hollywood blockbuster. This actually happened across the Northern Hemisphere in 1816, a year so climatically catastrophic that historians would later dub it the year without a summer. It's a wild piece of history that shows just how fragile our planet's climate really is, and how one volcanic tantrum on the other side of the world can bring humanity to its knees. But before we delve into the events of 1816, I'd like you to consider this. What would happen to our modern world if summer simply didn't arrive? Think about it. Our entire agricultural system, global supply chains, and economic structures are predicated on the reliable changing of seasons. Now imagine that predictability vanishing overnight, because that's exactly what our ancestors faced just over 2 centuries ago. Our story begins not in 1816, but a year earlier, on a remote Indonesian island, April 10th, 1815, a date that should be as infamous as any in history, marked the beginning of the most powerful volcanic eruption in recorded human history. Mount Tambora, a previously unremarkable volcano on the island of Sumbawa, decided it was time to make its mark on world history. After slumbering for more than a millennium, Tambora awakened with a vengeance. The initial explosions were heard over 1,600 kilometers away, in Java, where locals mistook the sound for distant cannon fire. British authorities actually dispatched troops, believing a battle was underway. But this was merely the opening act of Tambora's devastating performance. The main eruption came on April 10th, when Tambora literally blew its top off. The explosion was catastrophic, rating a colossal 7 on the Volcanic Explosivity Index, making it more powerful than Krakatoa and about 100 times stronger than the 1980 eruption of Mount St. Helens. The numbers associated with Tambora's eruption are almost incomprehensible. The volcano ejected an estimated 150 cubic kilometers of material, enough to bury London under 285 meters of ash. The eruption column reached a staggering 43 kilometers into the atmosphere, puncturing the stratosphere and introducing volcanic aerosols that would travel around the globe. Tambora's fury continued for 2 weeks, eventually transforming the once 4,300-meter-tall mountain into a 2,851-meter crater. In a geological instant, Tambora had gone from being one of the tallest peaks in the Indonesian archipelago to a hollow shell of its former self. But the true horror was unfolding on the ground. The immediate death toll on Sumbawa and neighbouring islands was catastrophic. Pyroclastic flows, superheated currents of gas and rock that can reach temperatures of 1,000 degrees Celsius, incinerated villages within seconds. The island's lush tropical landscape was transformed into a smouldering wasteland. An estimated 10,000 people were killed instantly by the eruption itself. What followed was arguably worse. The thick blanket of ash destroyed crops and contaminated water supplies. Severe food shortages ensued. Disease ran rampant through weakened populations. All told, an estimated 80,000 people would perish in Indonesia from the direct effects of the eruption. But Tambora's deadly reach was just beginning to extend across the globe. The sound of Tambora's eruption remains the loudest noise ever recorded in human history. The explosion was audible 2,600 kilometers away, equivalent to hearing a sound from London while standing in Cairo. If you were within 160 kilometers of the eruption, the sound waves alone would have been powerful enough to rupture your eardrums. But the most insidious product of Tambora's eruption was something the survivors couldn't see or hear: sulfur dioxide. The volcano injected approximately 60 megatons of sulfur into the stratosphere, a layer of the atmosphere where it couldn't be washed away by rain. This sulfur combined with water vapor to form sulfuric acid aerosols, creating a global haze that would reflect incoming solar radiation back into space. Earth's thermostat was about to be turned down, with catastrophic consequences that wouldn't become fully apparent until the following year. As 1815 drew to a close, people around the world noticed something strange happening in the skies. Spectacular sunsets painted the horizon in vivid shades of red, purple, and orange, a direct result of light being scattered by Tambora's fine volcanic particles, now circulating in the upper atmosphere. Artists of the era captured these otherworldly sunsets, not realizing they were documenting the visual prelude to an impending disaster. The full effects of Tambora's atmospheric tampering became apparent in the spring of 1816. Temperatures across the northern hemisphere plummeted. The northeastern United States and much of Europe experienced a dramatic cooling of 3 to 5 degrees Celsius below average. This might not sound like much, but consider that the difference between our current climate and the last ice age is only about 5 degrees Celsius. Small changes in average temperature can produce dramatic shifts in weather patterns, and dramatic they were. In May 1816, frost killed off newly planted crops in New England and eastern Canada. June brought heavy snow across New York, New Hampshire and Maine. On June 6th, snow drifts of up to 30 centimetres were reported in Quebec City. Imagine that, snow in June, in places accustomed to warm summer weather. Contemporary accounts describe people's utter bewilderment at seeing their breath condense in the summer air and watching snow accumulate on the ground during what should have been the growing season. July and August brought no relief. Killing frost continued throughout the summer months in parts of North America and Europe. In early September, ice was reported on rivers and lakes as far south as Pennsylvania. The growing season had effectively been reduced by more than half in many agricultural regions of the Northern Hemisphere. Here's a particularly incredible fact. On July 4th, 1816, while Americans were trying to celebrate the 40th anniversary of their independence, lakes and rivers were frozen as far south as northwestern Pennsylvania. People were ice skating in July. Let that sink in for a moment. The weather patterns weren't simply colder, they were erratic and extreme. The eastern United States experienced wild temperature swings, with frigid temperatures one day, followed by sweltering heat the next, only to plunge back into wintry conditions days later. One contemporary New Englander described it as a year of poverty when every green thing was killed. Europe fared no better. The summer of 1816 was the second coldest in the Northern Hemisphere since AD 1400. The United Kingdom recorded its lowest ever summer average temperature. Germany reported that the River Rhine froze over in August. Alpine villages, already living at the margins of agricultural viability, were buried under advancing glaciers and unseasonable snowfall. But the anomalous weather wasn't limited to cold. Weather patterns worldwide were thrown into chaos. While North America and Europe shivered, parts of the Middle East and Asia experienced devastating droughts. In China's Yunnan province, the normally reliable monsoon failed completely, leading to widespread crop failures. India experienced unusually heavy rainfall in some regions and drought in others, disrupting traditional agricultural cycles. Perhaps the most bizarre symptom of the climate disruption was the discoloured snow that fell across Europe. In Hungary, Italy, and southern Germany, brown snow descended from the skies. In some areas of Italy, red snow fell, leading superstitious locals to believe it was raining blood, a biblical omen of the apocalypse. We now know this coloured precipitation contained Tambora's volcanic ash, still circulating in the atmosphere nearly a year after the eruption, and thousands of kilometres from its source. The mechanism behind this global cooling is fascinatingly simple, yet profound. Volcanic eruptions don't cool the planet by blocking sunlight with ash. Most ash particles are too heavy and fall back to Earth relatively quickly. Instead, it's the sulfur dioxide that causes long-term cooling. When injected into the stratosphere, sulfur dioxide combines with water to form sulfuric acid aerosols that can remain suspended for years, creating a semi-transparent global veil that reflects a portion of incoming solar radiation back into space. Scientists estimate that Tambora's eruption temporarily reduced the amount of solar energy reaching Earth's surface by about 10%. This might not sound significant, but it was enough to decrease global temperatures by an average of 0.4 to 0.7 degrees Celsius. The effect was amplified at higher latitudes, explaining why North America and Europe were so severely affected. What makes Tambora's timing particularly unfortunate was that it occurred during what climatologists call the Little Ice Age, a period of already cooler global temperatures that lasted from the 14th to the mid-19th century. Tambora essentially delivered a knockout punch to a climate system that was already on the ropes. As summer refused to materialise in 1816, the human consequences quickly mounted. The most immediate impact was on agriculture. Across New England, the succession of freezes destroyed corn, wheat, and other staple crops. In some areas, farmers attempted to replant their fields up to 3 times, only to watch each new crop wither under unseasonable frosts. Quebec, normally self-sufficient in food production, was forced to import wheat from Great Britain. Even these emergency measures weren't enough. Food prices soared. Oats, which had cost 12 cents per bushel in 1815, skyrocketed to 92 cents a year later, a price increase of nearly 800%. Similar price spikes occurred across Europe, where poor harvests had been exacerbated by the aftermath of the Napoleonic Wars. The food shortages led to what would become the last great subsistence crisis in the Western world. Unable to feed their families or livestock, many New England farmers abandoned their homesteads and migrated westward, accelerating the settlement of what would become the American Midwest. This migration was so significant that some historians credit Tambora with speeding up America's westward expansion. In Europe, the suffering was even more acute. Switzerland, already reeling from the economic aftershocks of the Napoleonic Wars, faced catastrophic harvest failures. The resulting food shortages triggered its worst famine since the 14th century. Contemporary accounts describe people resorting to eating moss, cats, and boiled leather in a desperate attempt to survive. Ireland, with its heavy dependence on the potato crop, experienced widespread crop failures that foreshadowed the much larger Irish potato famine that would occur 3 decades later. Across France, food riots broke out as starving citizens demanded bread. In Germany's Württemberg region, government records show that many communities resorted to eating their seed grain, mortgaging their future harvests for immediate survival. The year without a summer claimed hundreds of thousands of lives through famine and related diseases. Typhus epidemics broke out in parts of Europe as malnutrition weakened immune systems. In Ireland alone, an estimated 100,000 people died from the combined effects of famine and disease. Global mortality figures are harder to establish, but some historians estimate that Tambora's eruption may have indirectly caused up to 1 million deaths worldwide, making it one of the deadliest natural disasters in human history. Here's a particularly grim statistic. In the summer of 1816, the death rate in many European cities doubled. In Manchester, England, church records show that funerals outnumbered baptisms for the only time in the city's recorded history. The demographic impact of the year without a summer would be felt for a generation. But the human toll wasn't simply measured in lives lost. The psychological impact of this climate anomaly was profound. Many religious communities interpreted the bizarre weather as divine punishment or a sign of the approaching apocalypse. End-of-the-world cults flourished. Church attendance soared as people sought spiritual explanations for what science couldn't yet fully explain. Contemporary diaries and letters reveal the deep anxiety that pervaded society. One Vermont farmer wrote, "People have experienced that depressing melancholy that the continued gloom of the atmosphere naturally produces." A Massachusetts clergyman noted, "The sense of an unusual and mysterious gloom prevailed. It was really a season of peculiar darkness and desertion." This psychological toll was compounded by the fact that people in 1816 had no understanding of what was causing their misery. The connection between Tambora's eruption and the climate anomalies wouldn't be scientifically established until the 1920s. Imagine the terror of experiencing what seemed like the end of the natural order itself, with no explanation available. In an ironic twist, the very technology that might have helped mitigate the crisis, global telecommunications, was still decades away from invention. News travelled at the speed of sailing ships and horse-drawn carriages. Many communities faced the climate disaster in isolation, unaware that the same phenomenon was affecting regions thousands of miles away. This isolation undoubtedly magnified the psychological impact of the crisis. While the immediate effects of the year without a summer were undeniably catastrophic, this climate anomaly also produced some remarkable and unexpected consequences that continue to influence our world today. Perhaps the most famous cultural byproduct of the year without a summer was Mary Shelley's Frankenstein. In June 1816, Mary Shelley, her future husband Percy, Bysshe Shelley, Lord Byron, and John Polidori were vacationing at the Villa Diodati near Lake Geneva in Switzerland. The persistent cold and rain forced the group to remain indoors for days on end. To pass the time, Byron suggested they each write a ghost story. From this literary competition emerged both Frankenstein and Polidori's The Vampire, a predecessor to Bram Stoker's Dracula. The gloomy atmosphere created by Tambora's volcanic veil had directly inspired 2 of the most influential works in horror literature. The dreary conditions that summer also influenced Byron's poetry, His poem, Darkness, with its apocalyptic imagery of a world without sun, was directly inspired by the eerie conditions of 1816. I had a dream which was not all a dream. The bright sun was extinguished, and the stars did wander darkling in the eternal space. The vibrant sunsets caused by volcanic aerosols influenced the arts as well. The distinctive yellow and orange skies depicted in many paintings from this period, particularly the works of J.M.W. Turner, reflect the actual atmospheric conditions caused by Tambora's eruption. Some art historians believe that the brilliant fiery sunsets in Turner's works from this period are accurate depictions of how the sky actually appeared during this volcanic aftermath. But the consequences of 1816 extended far beyond the arts. The agricultural disasters of that year sparked significant innovations in farming and transportation. In response to widespread horse deaths caused by a lack of oats, the German inventor Karl Dreiss designed the Laufmaschine, or running machine, the world's first bicycle. Initially created as a horse substitute, Dreiss's invention would eventually evolve into one of the most efficient forms of human-powered transportation ever developed. In the United States, the year without a summer accelerated the diversification of agriculture. After witnessing the vulnerability of traditional crops to cold weather, many New England farmers switched to heartier varieties or different crops altogether. Some agricultural historians credit this period with the expansion of potato cultivation in North America, a crop that would later prove crucial to feeding the growing nation. The westward migration triggered by the agricultural failures in New England had profound implications for American development. Thousands of farming families abandoned their homesteads in states like New Hampshire, Vermont, and Maine, seeking better conditions in what would become the American Midwest. This population shift accelerated the development of states like Indiana and Illinois, permanently altering the demographic landscape of the young United States. In Europe, the subsistence crisis of 1816 to 1817 spurred governmental reforms in food security and disaster response. Several German states established the first centralized food reserves specifically designed to mitigate future famines. These early systems would eventually evolve into the sophisticated food security programs that exist throughout the developed world today. The year without a summer also accelerated scientific interest in meteorology and climate studies. The puzzling weather patterns prompted systematic temperature recording in many regions, laying the groundwork for modern climatology. While the connection between volcanoes and climate wouldn't be fully understood for another century, the careful observations made during this period provided valuable data for later researchers. One of the more surprising economic consequences emerged in the whaling industry. As agricultural prices soared, so did the cost of plant-based oils used for lighting and lubrication. This price spike made whale oil comparatively more affordable, triggering a boom in the American whaling industry that would last for decades. The economic pattern set in motion by Tambora's eruption thus indirectly contributed to the near extinction of several whale species, before petroleum-based alternatives emerged in the mid-19th century. Perhaps most significantly, the year without a summer delivered a harsh lesson about humanity's vulnerability to climate fluctuations, a lesson with profound relevance today as we grapple with anthropogenic climate change. The events of 1816 demonstrated how even relatively small changes in average temperatures can produce dramatic disruptions to agriculture, economics, and society at large. When Tambora erupted in 1815, the scientific community lacked the tools to understand its global impact. Meteorology was in its infancy. The connection between volcanic eruptions and climate change wasn't yet established. People could observe the weather anomalies but couldn't explain them. Early hypotheses about the strange weather of 1816 ranged from the scientific to the bizarre. Benjamin Franklin had previously speculated that volcanic eruptions could affect climate, but this theory wasn't widely accepted. Some scientists blamed sunspots for the cooling. Others pointed to deforestation or even the use of lightning rods, which some believed were disrupting the natural electrical balance of the atmosphere. It wasn't until the 1880s, after the eruption of Krakatoa in 1883, that scientists began to systematically study the climate effects of volcanic eruptions. Even then, the specific impact of Tambora remained poorly understood. The full scientific explanation would require advances in atmospheric chemistry, fluid dynamics, and computer modelling that wouldn't be available until the 20th century. Today, we understand the volcanic winter phenomenon in great detail. Modern climate models can simulate exactly how volcanic aerosols affect global temperature patterns. We know that major eruptions can influence climate for 2 to 3 years before the sulfuric acid particles finally settle out of the stratosphere. We understand the complex feedback mechanisms that amplify the initial cooling effect, such as increased snow cover reflecting more sunlight back into space. What makes Tambora particularly significant in scientific history is its role as a natural experiment in climate forcing, a dramatic demonstration of how atmospheric composition can alter global temperatures. The lessons learned from studying Tambora have directly informed our understanding of other climate-altering mechanisms. Tambora also provides a sobering benchmark for assessing potential future volcanic disasters. Despite its catastrophic impact, Tambora wasn't even close to the largest volcanic eruption in Earth's history. The Toba eruption, approximately 74,000 years ago, ejected an estimated 2,800 cubic kilometers of material, nearly 20 times more than Tambora. Some paleoclimatologists believe Toba may have triggered a volcanic winter lasting a decade and created a population bottleneck in human evolution. Even within recorded history, Tambora has competitors. The 1257 eruption of Somala's volcano, also in Indonesia, may have been of similar magnitude to Tambora and contributed to the onset of the Little Ice Age. The difference is that Tambora erupted during a period of relatively systematic weather observation, providing scientists with a well-documented case study of volcanic climate forcing. The scientific importance of Tambora extends beyond climatology. The eruption created a natural laboratory for studying how ecosystems recover from catastrophic disturbances. When biologists finally returned to survey Tambora in the early 20th century, they discovered an ecosystem that had evolved in isolation, a miniature Galapagos, demonstrating principles of island biogeography and succession ecology. Geologically, Tambora provided valuable insights into the behavior of stratovolcanoes and the mechanics of caldera formation. The volcano continues to be monitored today as part of global volcanic hazard assessment programs. While another eruption of Tambora on the scale of 1815 is considered unlikely in the near future, the volcano remains active. A smaller eruption occurred as recently as 1967, and geologists continue to detect magmatic activity beneath the caldera. Perhaps the most important scientific legacy of Tambora is methodological. The interdisciplinary approach required to understand the eruption's global impacts, combining volcanology, atmospheric chemistry, climatology, history, and economics, exemplifies how complex Earth systems must be studied. This holistic approach has become the foundation of modern Earth system science. The events of 1816 raise an inevitable question. Could a year without a summer happen again? The answer, unfortunately, is an unequivocal yes. The geological record makes it clear that eruptions on the scale of Tambora, while rare, are recurring features of Earth's volcanic activity. In fact, there have been at least 30 eruptions of comparable or greater magnitude in the past 2 million years. Statistically speaking, we can expect a Tambora-scale eruption approximately every 1,000 years. Several currently active volcanoes are capable of producing Tambora-like climate effects. Yellowstone caldera in the United States, Taupo in New Zealand, and several Indonesian volcanoes have the potential to inject climate-altering quantities of sulfur into the stratosphere. While modern volcano monitoring can provide warning of imminent eruptions, we cannot prevent them. What would a Tambora-like eruption mean for our modern world? The impact would be profoundly different from 1816, but not necessarily less severe. Our globally integrated food system provides buffers against local crop failures, but also creates vulnerabilities through its complexity and just-in-time delivery methods. A significant global cooling would affect agricultural productivity worldwide, potentially stressing this system beyond its capacity to compensate. Modern agriculture relies heavily on consistent growing seasons and predictable climate patterns. The wild temperature swings and unseasonable frosts that characterized 1816 would devastate crop yields even with today's technology. Grain reserves in most developed nations typically hold only a few months' supply, not enough to weather a multi-year agricultural disruption. Our technological infrastructure would provide both resilience and vulnerability. Unlike our 19th century ancestors, we have weather forecasting, climate modelling, and telecommunications that would help us understand and respond to the crisis. However, our dependence on electricity, global supply chains, and computer networks creates new fragilities that didn't exist in 1816. Economic impacts would likely be severe. Insurance companies estimate that a Tambora-scale eruption today could cause global economic damages exceeding $4 trillion. primarily through agricultural losses, increased energy demands, transportation disruptions, and property damage from extreme weather events. The socio-political consequences are harder to predict, but potentially more destabilizing than the direct physical impacts. Food security is intimately connected with political stability. The Arab Spring protests of 2011 were partly triggered by rising food prices. A global food crisis caused by volcanic cooling could exacerbate existing tensions between nations and within societies. However, not all news is grim. Our scientific understanding of volcanic climate forcing would allow us to anticipate the effects and implement mitigation strategies. Unlike our ancestors in 1816, we would know exactly what was happening. This knowledge itself is a form of resilience that wasn't available 2 centuries ago. Some scientists have even proposed technological interventions that could counteract volcanic cooling. In theory, human-made stratospheric aerosols could be adjusted to compensate for volcanic cooling. Perhaps the most important difference between 1816 and today is institutional. We now have international organizations dedicated to disaster response, food security, and humanitarian aid. While these systems have never been tested by a global crisis on the scale of a volcanic winter, they represent capabilities for coordinated response that simply didn't exist in the 19th century. The Tambora example has directly informed modern volcanic risk assessment and disaster planning. Government agencies like FEMA in the United States and international organizations like the UN Food and Agriculture Organization have developed specific protocols for responding to major volcanic eruptions and their after effects. These plans include strategic grain reserves, emergency agricultural adaptations. When the skies finally cleared and temperatures normalized around 1818, the full scope of Tambora's global reach began to emerge in astonishing detail. The volcanic winter had literally reshaped parts of human history through a cascade of remarkable consequences that few could have predicted. What makes Tambora truly mind-boggling is the sheer scale of its influence relative to its obscurity. While virtually everyone knows about Pompeii, remarkably few have heard of an eruption that killed nearly 100,000 people directly and potentially another million through its climate effects. A volcanic explosion on a remote Indonesian island had managed to freeze rivers in Pennsylvania, trigger famine in Switzerland, and reshape artistic movements across Europe, all through atmospheric processes invisible to the human eye. The statistics surrounding this disaster stretch credulity. In parts of Europe, food prices rose by up to 800% in a matter of months. Some New England communities recorded temperature drops of 20 degrees Celsius below seasonal averages. Between 1816 and 1817, Vermont lost approximately 10 to 15% of its total population to westward migration, people literally fleeing the cold. Across the Atlantic, Switzerland experienced its highest recorded death rate since the Black Death. Even after temperatures recovered, Tambora's shadow lingered. Tree ring studies reveal stunted growth extending into 1818. The massive emigration from Europe to America during 1816 to 1817 permanently altered population dynamics on both continents. The literature born during those dark, cold days continues to influence horror genres more than 2 centuries later. Perhaps most fascinating is how long it took for humans to connect these global phenomena to their volcanic source. Not until the 1920s did scientists finally establish the link between Tambora's eruption and the year without a summer, over a century after the event itself. During those 100 years, the bizarre weather of 1816 remained a meteorological mystery, sometimes attributed to sunspots, sometimes to divine intervention, but never to its true cause, half a world away. Modern analysis has revealed other volcanic fingerprints from that fateful year. Ice cores from Greenland and Antarctica show distinctive sulfate layers, corresponding precisely to Tambora's eruption. Ancient tree rings from 5 continents display the same growth anomalies during 1816 to 1817. The geological record of lake sediments across the northern hemisphere shows distinct changes in composition during this period. When we step back and examine what happened in 1816, we're confronted with an extraordinary reality. A single geological event temporarily overrode Earth's climate system, disrupted global agricultural production, triggered mass migration, inspired literary masterpieces, accelerated technological innovation, and killed as many people as some major wars, yet remained virtually anonymous in historical memory until modern scientific investigation uncovered its fingerprints. The year without a summer stands as one of history's most bizarre climate anomalies. A time when summer snow fell across New England, red skies loomed over Europe, famine stalked millions, and for a brief moment, our predictable world turned utterly foreign. Tambora's massive geological tantrum had reached across oceans and continents to touch lives in ways beyond imagination, showing just how profoundly Earth's systems are interconnected in this vast planetary theatre we call home. And perhaps most unsettling of all, it wasn't even Earth's largest volcanic eruption, just the biggest one we've properly documented. Now that's a thought to keep you up at night. Thanks for watching. See you in the next one.